Hello, everybody. Welcome to our webinar with Snowflake on MindsDB. We have here myself, I'm Jorge Torres, I'm the CEO at MindsDB, and we have Miles Adkins, he's a cell engineer at Snowflake, and we have Patricio Cerda, I'm machine learning research engineer, my colleague at MindsDB too. And we're going to walk you through the importance that machine learning has in the roadmap of Snowflake. Miles is going to guide you through those insights. I myself am going to walk you into how MindsDB plays in that story, and Patricio and I will show you a demo on how to actually do forecasting for a real-time scenario or real use case scenario of the Chicago Transit Authority trying to forecast rides so that they can allocate the buses to different rides. So that being said, I'm going to hand over to Miles and welcome everybody. Please feel free to ask questions. There's a set of settings that you have on the right-hand side of this webinar. You can jump into the chat or ask questions, and myself and Patricia and Miles will make sure to answer them as we see them. And then at the end, some other team members from the MindsDB team will help you with questions, and we'll have some Q&A sessions.
All right, great. Yeah, thank you for the introduction, Jorge. Again, my name is Miles Adkins. I'm a partner sales engineer here at Snowflake, and I lead the technical go-to-market for Snowflake's AI and ML machine learning partners, which MindsDB is one of them. And yeah, happy to be here today. So to kick things off here, it is no secret that there is a transformational shift happening within the modern business world from the what and why that has happened to what will happen and how can we make it happen. There's been a lot of terms, AI, ML. It's really going from that business intelligence to this predictive modeling, supervised machine learning problem that we're going to explore here today. And Snowflake is really seeing this happen right before our eyes, given our spot as a cloud data platform and the plethora of questions that come inbound on how do we use Snowflake for data science, which we will dig into. When it comes to the data science maturity of our customers, which Snowflake has over about 4,000 of, we see a great range from customers, still trying to just get their first models into production, still exploring, what is this predictive modeling concept. And then we've seen, customers, that have hundreds of models in production with robust pipelines, automated, model retraining, model deployment technologies that consume a large amount of data on their Snowflake instance. And they're continually trying to even push us further on, hey, I need, better tools to support, this scalable machine learning function I have in my business. And that's awesome as well. And so today, what we look forward to showing you is how can Snowflake and MindsDB help you accelerate and get up this curve and start generating tangible business value, given your investments into your data infrastructure and your data talent. So with that, to kind of give you a quick overview of what is Snowflake and what makes Snowflake so powerful is Snowflake's unique architecture. Snowflake is comprised of 3 isolated layers that are all decoupled from each other, which in kind of traditional data warehouses, for X amount of, CPU that you wanted to add, you had to add more storage. And, you probably always weren't using your infrastructure as efficiently as it could be. With decoupling compute and storage, you really only have to pay for what you consume, either on the storage side or on the compute side. And so with that, at its core, Snowflake leverages cheap blob storage, which is unlimitedly available from Snowflake's 3 main cloud providers. You can deploy on AWS, you can deploy on Google Cloud or Microsoft Azure. The next layer we have is compute. Compute warehouses are available on demand where you only pay for what you consume, with the ability to scale up or increase the size of a warehouse, scale out as needed for a specific workload by turning that warehouse into a multi-cluster node. So you can think of, I have to take my team from 2 data scientists to 5, 10. How do I kind of scale out? We can do that through our multi-cluster nodes. And then lastly, Snowflake enables a third dimension, which allows you to scale across workloads as well by being able to spin up additional warehouses per a specific workload that you have. Therefore, compute is even decoupled from compute. And then lastly is Snowflake's cloud services layer, which enables Snowflake to be delivered as a service and encompasses all the unique features to the warehouse space. For example, data sharing for private and public data exchanges, security and governance with security-based access controls and row-level security, a bunch of metadata that enables extreme query pruning, driving query performance, etc. And so with this architecture enables what we call the Snowflake Cloud Data Platform, where Snowflake can execute on 6 distinct workloads, data science being one of those, where you can take your structured, semi-structured, and unstructured data, perform your data science workloads, and then deliver those to data consumers, whether it's a BI dashboard, a application that sucks in model predictions, etc. And so the way that Snowflake thinks about data science is summed up here in this machine learning lifecycle diagram, which is probably very similar to what is out in there in the industry. A lot of the data science lifecycle here can actually be run natively inside of Snowflake, whether it's collecting data from either batch sources or streaming sources, possibly through a Kafka connector or using our own Snowpipe. You can do a lot of visualization and understanding your exploratory data analysis using Snowflake Snowsight, or you can also offload those to a BI dashboard such as Tableau, which you'll see here today. You can do all of your feature engineering and transformation. So if I wanted to do some simple joins, filtering, data prep, you can push that down into Snowflake's compute engine. Where Snowflake relies on its partners, and here we'll see MindsDB today, is really on that model training and model deployment side. You currently can't train a model today inside of Snowflake, and so we push that out to our partners to fill the gap in the machine learning lifecycle for us. And then for model evaluation and model management, again, we don't allow you to deploy models that can be consumed live. We do have we are starting to roll out the ability for you to score batch models through our Java UDF new functionality that just came out. But for a more robust monitoring platform, we kind of act as the data layer where, again, we rely on our partners to kind of be the orchestration layer for any sort of kind of model monitoring platform. So with that, I'll throw it back to you, Jorge, and let you walk us through democratizing machine learning.
Thank you, Miles. Thank you so much. And I think that this resonates very well with the vision of MindsDB of the world of data science. And in the journey of democratizing machine learning, we also understand that we don't want to reinvent the wheel if there are players that do it excessively well. And we believe that Snowflake is probably the best tool out there for data preparation when you're kind of aggregating large amounts of data. And there's no reason why anyone should be reinventing this. And that's why we decided to partner with MindsDB, and the reason why Snowflake MindsDB partnership makes sense. So let me walk you through the problem as we saw it initially, and how these two visions of the world kind of merge into one same point. This is a machine learning lifecycle, as most of you see it, and probably a way to visualize that table that Miles was presenting, but more like into 3 basic building blocks that are kind of like intertwined with each other, kind of like subsequent of each other. You have the data preparation, the modeling, and the deployment. The problem is that today, most people learn machine learning how they would do some sort of research, either because you learn it on like a university, or because you took a class in Coursera, or any of these kind of like amazing tools and platforms that teach you how to do machine learning. However, you still treat applied machine learning the same way that you treat research in machine learning. And they should be two different problems. Like, one is when you actually want to move the needle of understanding of how you do machine learning for a specific task, and you want to increase for a known problem the accuracy or some quality metric. But then you have all of these problems that exist in companies today, which are more about taking the existing capabilities of machine learning, applying them to the problem that you have at hand, and getting results that are tangible and actionable and can actually give a return of investment to the companies that are pursuing those endeavors. And it seems that there's some dissonance between how people do research and how people are supposed to apply machine learning. And what we started to understand is that that dissonance starts with the fact that most machine learning practitioners learn machine learning from kind of like an ideal data frame or an ideal version of the data. And that's the same way that they tackle and apply machine learning problems. So they start with a pandas data frame that starts with a file, and they start massaging this data on pandas usually. And once they're done with the actual data preparation, then they can start doing the modeling. However, this makes this problem a little bit not intuitive when you want to move into production. And the reason for this is that you have to end up reinventing many different silos of well-known processes within data science and kind of like computer architectures. The problem of treating machine learning as a building block within the application layer is that you start with this file that then you transform into an ETLing process. So you build like this pandas workflow, and now you have this ETLing process from where the data really existed to how the data is supposed to be taken by the model. And either you kind of like automate this ETLing process yourself, or you use tools like Airflow and whatnot to make this process for you. However, it doesn't make sense in most cases for you to do those transformations if the data is coming from a database. Likely the database knows how to do these transformations a lot better, and you don't have to kind of like extract all the data and then do all these transformations in memory, when the database itself could be probably the right place to do it. Now, the second part that you end up reinventing is how do you expose this model so it can be consumed in production. Most people end up wrapping these models around the web service, and this has a few disadvantages too, which is now you have to maintain that infrastructure, and you have to maintain not only the model is running, but is running all the time, and that the model is consuming data from that ETL pipeline. Lastly, your model living in a web service, it is very hard for the applications to now consume this model in a native way. You have to now build a new interface that will consume data from that web service, deal with whatever layers of authentication and all the different processes that you now have to put in place to extract the predictions and put them back where you need them, either in the application or the data warehouse, data lake, so that you can actually use those for forecasting or like the actual problem that you're trying to solve. And this also makes it the problem is unpredictably expensive, time-wise and resource-wise. You don't know ahead of time how much it's going to cost you to build a model. You don't know the people involved and the amount of man hours that you have to put into this particular problem. And then once you have the problem, you don't know the cost of infrastructure associated with the problem itself. So this life cycle of machine learning as an application needs to change. And in general, the problem review as we see it today is that perhaps every machine learning problem, applied machine learning problem, should start where the data lives and not in the machine learning modeling parts. And I know that as a machine learning practitioner, we're eager to jump into the problem of building the model, and we start kind of like massaging the data in this kind of like process that perhaps is not the ideal one. We should start with where does the data live? What are the transformations that I can make in this database? And then once I have the data, the machine learning model can be either automated or built upon the process that starts where the data is. And that's the way that we see this problem. And that's where Snowflake also agrees with us in the world. They understand that Snowflake in itself is an enabler for that first step of machine learning. And we buy into that philosophy too. We also buy in the fact that data preparation, which is the most difficult part of the machine learning lifecycle, is solved. It's a solved problem by Snowflake, and there's no reason to reinvent that. And beyond that, SQL is probably the best feature engineering tool that exists out there. You know, you send a query to the database and you get columns in return. Those columns are features. From there on, how you kind of turn those columns into vector representations is more like an encoding problem that could be automated. But the actual process of extracting the meaningful information into columns, you can do through SQL. And again, Snowflake is an exceptional tool for that. There's literally everything that you need to do with your data you can do with Snowflake. So if your data is already in Snowflake, you've already solved the data preparation side. You've already solved the data acquisition, the data cleaning and labeling. You know, the fact that Snowflake will make you treat data as tables, that means that you have to kind of think of some data types and organize this data, and it provides the tooling for you to clean up the data as you move up the stack of kind of like preparing your schema. And then you have SQL as a feature engineering tool. So if the data preparation part is solved already, which is the most difficult one, we had an idea ourselves, and it's why don't we enable the same capabilities for modeling and deployment, everything through SQL? And that is the question that we decided to solve. And for that, we came up with a concept called AI tables. And AI tables allow you to summarize all of the machine lifecycle beyond the data preparation, all within the data layer. Let me walk you through an example that will sink in some of those ideas. Imagine that you have a simple table. Of course, in databases, tables don't look like this, but you have income and debts. And if you were to visualize this, you will see what you have on the right-hand side. Each column, each row is a data point in this graph. Now, the way that databases work is that if you make a query and you hit an exact point or you hit an index, you're going to get a response. But databases are not built to return approximations when you query something. So even if you query for a where statement that is very close to the data points that you have, you're not going to hit an index, or you're not going to actually return anything or get nothing in return. And that's just because that is the design of a database in itself. Now, everyone that has built a machine learning model before understands that you can build a hyperplane, and you can then train that hyperplane to fit the data, or you can adjust the parameters of that hyperplane to fit that data. And the idea that we had is, well, let's create a syntax that will enable anyone that is aware of SQL to create those hyperplanes create and train models in a way that is very similar to what you create a view database view. And the syntax is very similar. You create predictor, you name the predictor, you tell it from where you want to train this actual predictor and what you want to predict. And of course, this dialect can be extended, and MindsDB allows you to then pass more parameters so you can define, okay, how do you want to encode the data? How do you want to mix this data? How do you want the model to behave? What are the parameters that you want to pass? But if you don't know anything, or you actually want to start with like the AutoML part, MindsDB enables this off the bat. And then what you can do is you can query that line, or you can query that hyperplane the same way that you query a table. So you select the parameters you want to select from that model, and then you pass whatever you pass on the where statement is the input for the model itself, and you can get that approximation. So that intuition allows you to treat the modeling part in SQL. And then the interesting thing about databases is that there is not really a concept of deployment. As soon as you do create table in a database, that table exists and is live in the database itself. And the same thing happens to creating a model as a table or creating a predictor. As soon as you do that command of creating predictor, that table is being created and it's ready for you to consume as soon as it's done. So the process of deployment is already simplified by doing this AI tables abstraction. Now, I think that the interesting part was this abstraction makes sense, but as we started dealing with databases, we started to realize that there were very difficult problems, even for machine learning engineers, that are very common in databases. And let me walk you through an example that will hopefully convey those problems. Imagine that you are a data analyst at the Chicago Transit Authority, and you are tasked with being able to optimize the number of buses per route. And the reason for this is that some days you allocate a given number of buses to routes, and what you do is you do this based on the average number of rides that you see and observe on the routes. But sometimes those buses are overpacked, or they cannot fill the amount of passengers that you need, and then sometimes those buses are extremely empty. And the reason for this is that some of those routes fluctuate a lot over the week, over the month, and you actually want to use all the data that you have to be able to forecast into the future using machine learning. So you want to apply machine learning to forecast the number of rides, and then do your optimization way better than just hand guessing or kind of like doing it based on the average. And that is exactly the problem that we're going to walk you through. The best way for us to jump into that problem, also, we want to understand or convey to you what are the things that make this problem difficult. In this particular table, you have timestamps associated with each of the rides. And this makes it so that the information that you need to forecast rides is not contained in one single row. It's contained in multiple rows. And when there's a timestamp, then what this means is that you're dealing with a time series problem. Time series problems in itself are really difficult to solve. But in databases, time series problems have extra caveats to it. You have extra columns. In this case, you have a column that says type and tells you the type of the day, but you can have other columns that's probably the value of the ticket at that given time. So databases in itself, as you start aggregating information, you have those timestamps, so that makes them time series, but you also make them multivariate by the fact that you usually don't just have one column. And something even more complicated is that you have partitions associated to it. So in one single table or one single view or the result of one single query, you just don't have one single time series problem. You have as many time series problems as partitions you have. In this case, you have different routes, and that means that a group of time series are associated to just one single route. And this makes the problem of high cardinality. So solving time series problems that have multivariate, that are high cardinality, and solve them in an effective way is a problem that is difficult for machine engineers. And then moving those actual models into production involve a certain degree of skills that make these problems not just very complicated, but very difficult to move into production and to maintain. So let's walk into how you can actually solve this problem in a very simple way with MindsDB and Snowflake. And then my colleague Patricio will show you how you can visualize all of this in a BA tool like Tableau. Okay, let's start from the basis that you have MindsDB running either on your cloud, your computer, or that you're actually running through the MindsDB cloud. Again, MindsDB cloud is the same thing that you find in MindsDB open source. It's just that we manage it for you, so you don't have to deal with that. And it's actually very convenient. Once you log into your MindsDB cloud graphical user interface, you can actually create a database integration. MindsDB supports the same parameters that you pass that you will usually see in any client that supports Snowflake. So you specify the database. In this case, we're going to connect to the Chicago Transit Authority database. You specify the host, the port, your account, your warehouse, local query is usually the one that you go for, your schema, and then you pass your actual Snowflake credentials. Once you do this, then you can start playing with MindsDB, connecting to it from any MySQL client, because MindsDB speaks to MySQL protocol, and happens to be the coincidence that most clients that support MySQL also speak to Snowflake, and therefore you're probably going to be using the same tools that you already use. And in the following example, we're going to use DBeaver as one of the most popular ones. And in 3 simple steps, I'm going to guide you through the process of visualizing the data you have in Snowflake, as well as to create a model for the task that we have in hand, which is forecasting the number of rides in a particular route or particular routes within the Chicago Transit Authority. And then my colleague Patricio is going to show you how you can visualize all of this in a tool like Tableau. So let's jump into DBeaver and let's start solving this problem. Okay, here in DBeaver, you can connect to MindsDB and you pass the same type of credentials that you usually pass to any MySQL client, where you connect to. So you guys lost audio? Where you connect to, in this case, my cloud account and logging in with my MindsDB cloud credentials. And once you do that, you can start running queries into MindsDB, normal queries, SQL queries, and some extension of those queries to actually do machine learning. So I'm going to break this into 3 simple steps. The first one is your training data. And in that one, we're going to start by visualizing the databases that we have in Snowflake. So let's look at this. MindsDB ships with 3 simple databases. The first one is the information schema, where you can get information about MindsDB server as a whole. You have the MindsDB database or the MindsDB schema, where you can see metadata about the predictors that you train or the models that you train, as well as to access each of those predictors as tables. And then you have data sources in case you want to upload files. You're not necessarily connecting directly to a database, or you want to mix information that you have from a database with information that you have in some files. And in this particular case, the integration that we created from the graphical interface, the Snowflake one. And let's see the data that we have there for this problem. So I'm going to switch to that database. And then I'm going to explore the public CTA bus rights data that we have. And let's see how that is going to be useful for our problem. This table has a few columns. It has route, date type, and rights. And if you can see, this particular table has the specific number of rights per route throughout time. And then also another column that tells you if that day is either a weekend or a weekday. We're going to use this table to actually train a model to forecast that number of rights, so that we can actually make a proper forecast of how busy a particular ride is going to be, and therefore how many buses I should allocate to that route. So the second step is to actually train a predictor. MindsDB makes this very simple. Even though your information can be a very complex time series problem, in this case multivariate with many different partitions, as we described before, MindsDB simplifies this in a syntax that makes it as simple as when you create a view or a table. So let's explore this a little bit more. Let's switch back to MindsDB and see what's going on there. We're going to see the tables that exist in MindsDB. And MindsDB comes with, or ships with, 2 tables, the commands and the predictors. Predictors is the one where you can see the status of the predictors or models that you're training. And then every time you train a new model or predictor, you're going to see them as a table here. Let me show you how the predictors look like. For this particular example and this particular demo, I have already a pre-trained predictor for the number of rights given the table that we have of CTA bus rights. And the reason why I'm doing this is because usually time series problems and time series models take a little bit to train. And for us not to wait a few hours to get this all done with, we're going to train a new one, but we're going to use the one that I have already trained for the case of this example. Now, training a model in MindsDB is as simple as creating a view or another table from a table. And the syntax is very simple. You specify the name of the predictor. In this particular case, we're going to tell it that it's going to be called rights predictor _ tests. And then you specify from what data you want to learn from. In this particular case, we want to learn from that table that I showed you before, which is the CTA bus rights latest. And since that table contains information from all the way back to 2020 or January 2000, you actually probably want to train a model just from like the last 20 months. And that may be way enough data for you to actually solve this problem. The next thing that you want to specify is, of the columns that you have in that table that you're training from, what is the column that you actually want to forecast? So we're going to forecast the column right. And the next thing that you're telling MindsDB is that this is a time series problem. Essentially, that the information that you need to forecast is not contained in one single row, but in multiple rows, and that you can organize those rows by the column date. And not only that, but you're actually having in this particular table many different time series. And you're going to discriminate each of those time series by a partition. And the partition is defined by the values on the column routes. The next thing that you want to do is you actually want to take into account just the last 10 rows for every given prediction. And that is what you define as the window. And for the problem that we have at hand, we want to forecast for the next week, so the next 7 days, and our horizon is 7. So let's run this query. What MindsDB does behind the scenes here is that it tries a few different models and a few different building blocks to build your predictor. And this is due to the powerful automatic capabilities that MindsDB has. But if you're dangerous enough and you know what you do in machine learning, or you actually want to tweak them, MindsDB allows you to change the behavior of your model as well as all the hyperparameters. But for now, and for this simple example, we're going to go for the simple syntax where you let the AutoML drive it for you. And in the back, MindsDB is training the model. Let's see that that is actually happening. What you can see here is that we have the model that we had already pre-trained, as well as the new model that is training right now, writes forecaster_test. What we want to do now is use that actual model. And the third step is very simple too. You actually have data in your database that now you can join into the model, or you can query this model with a where statement. Given that this is the time series problem, you actually want to join it with the table that has the historical data. So in this particular case, you're going to join the table CTA boss writes latest with the predictor that we just trained, which is the writes forecaster demo. And what you want to do here is you actually want to also forecast for when the date is greater than latest. This greater than latest is a syntax that MindsDB provides for you, so you don't have to go and actually fetch the latest information. MindsDB knows that it goes to the latest of your data set and pulls the window of information as you define to be the window when you train the model, and uses that to actually make the forecast. And in this particular case, we're going to train for, or we're actually going to forecast for route 171. Again, running this should be very simple. And this is very powerful. You know, in one single statement, you've managed to use a trained model that also combines the information that you have in your database to forecast into the future what would be the amount of writes or the projected number of writes that you will have for the next 7 days for this particular route. And you can do this for other routes. Let's pick route 19. The beauty of this is that MindsDB abstracts all the complexity of model building, model deployment, all through SQL, which allows you to think of the data that you want to use, train models using the same syntax or a very similar syntax that you're actually used to when you create a view. And lastly, you can join these predictors with the information that you have without thinking too much about data preparation, especially when it's time series. This can be a daunting experience. I'm going to hand it over to Patricio because he actually is going to help you visualize where the routes are very difficult to forecast, and then use this forecast that MindsDB is generating into the same visualization so you can see it all end to end as if you were a BI user in a tool like Tableau.
Okay, thank you, Jorge. Here in Tableau, this is a new project. We're starting from scratch, and the first step is to actually go to the Connect tab and do a direct connection to Snowflake. This is the same host as Jorge was using, so I'll just put the password here, and there we go. We'll be using the local query warehouse, nothing special. The database will be the Chicago Transit Authority one, because we have all the information there, including pre-saved output from a pre-trained predictor, which is what we want to visualize. So the way this works in Tableau is we need to actually join all the relevant information in our data source. So the first table is the actual writes that happened for each. So you can see down here, for each route, we have a specific day in time, and it goes all the way back to 2001 with a certain type of day. So if it's a weekday, if it's a weekend, a holiday, and then the actual amount of writes that were seen on that route on that day. We will join this table with the stops by route view. We will join on route, the route column, and this view has useful information because for each route, it has all the stops for that route with their latitude and longitude. So, well, and of course the route volatility. And we will be using this to plot it on a map visualization. Finally, the forecasts by MindsDB. In this case, we will also join on routes. This table has the observed value for like the observed rides for a certain route on a certain day, and it has information regarding the prediction. So not only the forecast, but also like an associated confidence level with a lower and upper bound, and whether the actual observation was anomalous or not according to the predictor. So we now have everything we need. We just have to open a new worksheet. And just to go through the motions of seeing what route is where, we can take the longitude and latitude and just put them here on respectively on columns and rows, making sure that this is measured as a dimension. And we should probably get the size of the blobs to a smaller size so that it's readable. Actually, I'll just zoom in a bit on a specific part of the map. I actually wanted to move, but I can't find the tool to move because I want to concentrate on like this part right here. Okay, that's fine. You'll note that like if we take a closer look at one intersection here, there are like pairs of routes, right? And it turns out that this is actually expected. Like for each street, there are two directions. So what you're seeing here is the stops that are in front of each other, but at slightly different positions. So it definitely checks out. Okay, let me just recenter. We can add the route number as a mark, and we can assign a color to each different route, like this. So, well, maybe having a bigger blob size can help here. And so you can see more or less where each route is on the map. So let's say you want to exclude and only see the route number 6. Well, there you go. Route number 20, and so on. But we can also, like, we can remove this mark and instead add the volatility. And if we mark this as an attribute and assign color to it, sorry, here, we now get a sort of heat map that indicates to us like the darker blues here are routes that are more volatile. We can also add the same filter, but as a true filter, and that way if we add like the complete range of possible volatilities, we can actually show the filter in the right-hand side and maybe say that we want routes that are particularly volatile. So let's say that should be enough. We have a handful of routes here that seem to be more volatile than most. So, you know, there's routes. Oops, we don't have route information. Let's add it. So let's add the route again, but this time detail, that's the name of this icon. That's enough because if we hover over something now, we have the volatility, but also the route itself. So there are a few here that are the most volatile on Chicago, it seems. So for instance, Route 11 seems to be pretty volatile, right? And now you might be wondering, like, okay, those are probably more challenging to plan for. What do MindsDB predictors think of this, right? And actually, what does the MindsDB predictor think of this? Remember, we just trained a single model. Let's see. So if we take the timestamp and we assign it on a new worksheet, right? Defining the time granularity at day level, so a daily timestamp, and then we add the actual amount of writes that we're seeing. This is the aggregate, like this is of the entire Chicago city, the amount of writes that were seen on, like, from January 1st, 2020 to August 30th on the last year. So we actually can just like take what MindsDB thought at a global level as well, and we can see how they compare. And it turns out they compare pretty well. Like MindsDB was able to forecast decently, but of course, this part of the year was when the first lockdowns happened, and clearly the MindsDB predictor thought that the usage might go up at any moment, but it instead kept decreasing, right? So this is like an anomalous situation, and you can actually check this is the case by adding the lower and upper bounds. This is way too colorful, so let me just edit the colors so that the lower and upper bounds are more like gray. That's better. Now, if we zoom into this relevant bit here, you'll see that the blue line, which is the observed amount of writes, actually falls outside of the bounds starting March 16th. And it takes a while, like I would say maybe 2 weeks, until it again, like the predictor starts coping with this like new reality, right? Or way of the new mode of working that the routes in this transport system are behaving. And then once again, the true values and the predicted values are in line with one another. So that is pretty interesting to see. And of course, the values, like the timestamps where the actual value falls outside of the bounds, are flagged as anomalous. So you can set up your pipeline to monitor for that Boolean flag. And whenever it's true, you know there's something like this that might be going on. Now, at the end, you'll notice that the blue line suddenly stops, and then you've got the actual forecast that MindsDB produces for the next 7 days. So if you assume that the present time is August 30, 2020, so basically almost a year ago, then this means that there we go. The following 7 days are, at least MindsDB thinks, are as this orange line here. And this is globally speaking. But remember, we can, and in fact are, predicting at a group level granularity, which means we can actually group by route, and the forecasts are still there, like at each individual route. So let's do that. Let's add the route as a filter. This is okay. And let's show the filter. So if we select all routes, we get what we were seeing before. No surprise there. Let me just remove the upper and lower bounds to unclutter this graph here. But if we go back to the map, the original intention of us was to show route number 11 because it seems to be quite volatile. So if we go here and we just disable all but keep the route number 11, there we go. Okay, so this is how it looks. So MindsDB thinks that the prediction for the next 7 days is going to be like this. A little bit noisier. And in fact, you can see in the behavior of the series, there are some odd spots like this one, where there seems to be some sort of spike, right? So quite interesting. If we go back to the map and maybe take this route or this one, or like route 73, which is less volatile, right? 0.41 against 0.67. We can easily just toggle the switch. And there you have it, forecast for an entirely different route. In this case, there's a peak here instead of up here on the previous case. Just to finish, we can, I don't know, do one that's more volatile, but route number 1 might be a good candidate. So if we go to the worksheet and select it. Okay, so actually this is interesting because the behavior of this one is much more erratic, and you can see our predictor is not doing as well as in the other two. If we include the forecast bounds here, this is quite interesting. You'll see that they are much wider, and this happens when your predictor is less confident, right? So it makes sense that this is the case. In this case, it might be conservatively too wide, and this can be adjusted in the predictor settings, but it still is quite interesting to see. So yeah, this is an example, a very brief example of how you do predictive analytics with this combination of MindsDB, exposing the results to your Snowflake database, and then plugging this into Tableau to see the results and basically forecast for any route you want to forecast. So yeah, I hope this has been interesting, and I'm looking forward to solving any questions that might come up in the Q&A session. So thank you very much.
Thank you, Patricio. This was a fantastic guide through all the way from your data in Snowflake to actually being able to see your forecasts in Tableau. I think that for now, we're going to jump into Q&A. And the next steps, of course, for us would be that you please join the community and that we are there to help you in any of the projects that you have. I know that in the chat is becoming quite active right now, and some are asking questions as to some specific problems that you want to solve at the data layer, and that's what we're here for. We essentially want to make sure that the problems that you're trying to solve in machine learning, applied machine learning for that matter, is something that MindsDB can excel at, and we are very excited to have you here. Patricio, if you have, or Miles, if you have any other comments, otherwise we can just jump into the questions.
So I guess let's jump into the questions.
Yeah. So one of the questions that we've been getting is, are we going to provide a certificate of attendance for the webinar? We are not. We didn't think of this, but certainly we can send you a confirmation that you were in the webinar, and then for future webinars, that's something that we can do. Yeah, thank you for that question. Really.
Yeah, I saw one question here. Can Snowflake execute Python pipelines? And it's something that we're currently working on. The feature name is called Snowpark. Currently, we have Snowpark for Scala, where you can actually code in Scala, and then all that work will be pushed into Snowflake. This is a great place to do a lot of your feature engineering, kind of data prep step, where as opposed to writing some pretty nasty SQL, you can just, again, program in Scala. Python is on the roadmap next, and so we hope to have something out there in the next quarter or two where you can kind of program in a PySpark-like API, but all that work can be pushed into Snowflake.
So lots of questions. Is it possible to configure the model, and how? It is possible to configure the model. So we've tried to make Lightwood, which it is like our machine learning core, as customizable as possible. So the philosophy behind it is to design different machine learning modules that can be implemented at all the steps in the pipeline. So you can implement like a custom data cleaner module. You can implement a custom cross-validation module if you want to, even though for time series that's not the default behavior. You can implement those things if you have the capabilities of doing so, and then just specify this when building the predictor code, like using the graphical user interface or from SQL. So the idea is to be as customizable as possible, but if you don't, if you're not interested in that, we try to come up with the best default configuration. So in that sense, we are, pretty automated compared to the other AutoML solutions in the market. So I think that was like 2 questions at once, but yeah.
So there's another question of from Sheikh Qadir about R and Python being the de facto languages to do machine learning. We agree with that, and many of the models that MindsDB runs behind the scenes are in Python. However, not everyone is either capable of building very sophisticated models, or the ones that are very capable as well of doing them, they may not have the time to produce them. So MindsDB tries to make this abstraction for that great majority of users that have access to data and would like to get a forecast without having to build the models on Python. They can just build them in a SQL syntax, or as Patricio was sharing with you, in a JSON kind of simplification of a dialect, what is called descriptive machine learning. And then it opens up the door for those that want to build specific building blocks. So essentially, if you are a machine learning engineer and you want to contribute some specific either encoders or models or model building blocks, MindsDB comes with this framework called Lightwood, which allows you to publish those in a very similar way to kind of like this modular architecture that we have for applied machine learning. So long story short, we still believe that Python and R will continue to be solid tools for building machine learning blocks. And we want to enable that capability for those that want to. And then we want to provide this abstraction for those that want to actually think of the data as a problem, and then the blocks that they use more like a Lego solution where they can decide, okay, for that specific problem, I can either let MindsDB to use the AutoML capabilities, or I can tweak how I want those blocks to be assembled.
So regarding time series predictions for data streams, we do have connectors to Kafka, and I think I'm forgetting the other one, Redis, right? And there's a special flag you can activate when doing the query to signal that this is actually consumed from a stream rather than a table. And so yeah, and that changes a little bit the behavior, in the sense that you're now predicting constantly for the actual time step instead of maybe for historical data, like in the demo. but it's certainly possible. So if that's your use case, we're very interested in knowing how we can help further. Also, MindsDB can use transformer models for time series. We actually have a transformer encoder right now. I don't think it's the default, but you can specify it at when building the model. And as for the the actual forecaster, because we have like a three-way stage model selection phase where we actually encode the data, then we generate a model that consumes the encoded data, and then that prediction is decoded back. So for the encoder side of things, we actually use a transformer. But then for like the model itself, we haven't tested transformers yet. So actually, if you're interested in contributing, maybe that could be a very interesting thing to do. The space for customizing it that way is certainly there.
There is a question from Ashwin J about how does MindsDB AutoML capability compare to other AutoML solutions in the market? And the question, or the answer to the question is, it depends on the problem. For time series, MindsDB is certainly the most like advanced solution for multivariate time series with constraints of cardinality, as well as being able to real time. In that sense, MindsDB AutoML capabilities can outperform most of what you find out there. And when it comes to other non-time series problems, we're actually about to publish benchmarks with like other popular machine frameworks, and MindsDB stands on the top ranking of those benchmarks. And these are benchmarks that are not produced by MindsDB, but by like a third party. And we just decided to participate now in this competition. The result that we're getting are quite impressive. So all in all, MindsDB is a wonderful tool for AutoML. But remember that the main value added of MindsDB is that you can either bring your own models if you want, and we'll definitely have a webinar about doing this on yourself, so you don't have to rely on MindsDB AutoML capabilities. You can even integrate other AutoML frameworks, but then you can create this abstraction so that you can consume and create those models straight from your database and from data in your database and back. There's a question from Constantine about, can the model generated by MindsDB be automated manually? So you can certainly re-update or retrain the model as many times as you want. The next version of MindsDB is releasing with a capability for you to define a threshold for retraining, or a retraining policy. And that way, just since you're training from a query, and assuming that that query is a moving kind of like live corpus of data, then all of what MindsDB does is that it just essentially defines that frequency and retrains it. The same way that some materialized views work, where you define a frequency in which you want to rematerialize the view. So similarly to that, we are enabling that capability to some of the models that you can generate in MindsDB. Let's see what other questions are there. Patricia, you want to take the cross-validation question?
Yeah, I actually touched upon this one before, but basically the answer here is we have an analysis phase where we do like a single fold validation. That's like the default behavior, but we do divide the data into folds. There's like internal logic that enables that. And if you want to personalize this, it's easy. It's not currently the default behavior, but it can be done. Now, having said that, for time series tasks, this is not the case because the data has to be split in a different way. And we can do what is the analog of cross-validation for time series, but it's not being done yet. So for time series, this is not, you can bring your own module for that, but it's not the current approach.
Calvin, how do you determine which machine model is being used? MindsDB like the next version that we're releasing with MindsDB has a describe to a model. So the same way that you describe on a table, you describe a model, and it can describe to you what was used to generate the model. Similarly to that, you can explore this information in the graphical user interface. But that is a great question, and I think that that is one of the areas where we will continue to innovate as to finding that right balance of what is the most relevant information that we have to provide for you when the model is being generated automatically, as well as what is the information that you need if you actually want to go and tweak the model yourself. So building your models, customizing your models is the centerpiece for the next release of MindsDB. And we'll love to, of course, share as much of that, and we will point to some of the documentation related to those upcoming features once we release the video. We unfortunately ran out of time. There's a few questions, of course, that we were not able to complete. But what we're going to do is we're going to, of course, as we publish this video, we're going to publish a tutorial for you to kind of like follow through the demo that Patricia and I walk you through, as well as to answer those questions that we're not able to get to answer. Thank you, Miles. Thank you, Patricia, for joining us on this journey, and again, Miles, for all your support. I know you've been a great champion for what we do.
Thank you, guys. Talk soon.
Thank you too. Bye-bye.